for the tutorials next week. You never know, we might even get people up at the board or the visualizer demonstrating their solutions to these. They so volunteer. Why is that hovering in the middle? Okay, so I think I'll kick things off by solving this one, or giving the proof solution for this one, and then we'll talk. See, there's another similar one. So the first one we did was just the sum of the integers up to some point n. This one is the sum of the squares up to n. There's another one there, the sum of the cubes up to n. Which, interestingly, the sum of the cubes is actually the square of the sum of the integers, which is kind of nice. But you can also immediately ask the question, well, what's the generalization of this? You know, in each case here, you've got some kind of polynomial for the sum of the integers, or the sum of the squares, or the sum of the cubes. The upper limit 10, you know, how might you go about discovering these polynomials, or how might you go about explaining them a bit more? So after we've solved the second one, we'll have a look at that. Okay. I'll log in there. Okay. Oh, my paper. Let's use this paper. Okay, so we're going to look at problem 2 there. So I'll switch over to the visualizer. So I want to prove this formula that the sum of the squares, when you start at 1 and proceed up to some integer n, that this has a nice formula in terms of n. It's 1/6 of n plus 1 times 2n plus 1. And moreover, this holds for any integer n. Any integer n greater than or equal to 1. Wouldn't mind just shutting the door there. Just keep the chatter out. Thank you. Okay, so now with these proofs by induction, you know, kind of half of it is done for you already, because half of it is just kind of a template. You can almost pick up a big rubber stamp and stamp down the scaffolding, because you can do it without thinking. We always need to establish the base case. Where is the base case? Well, the base case is the starting point of my statement. So the base case is when n equals 1. You know, almost always the base case is just a simple observation. Because what's the sum of, when n is equal to 1, what's that equal to? Sum of j squared from j equals 1 up to 1. Sorry, oh, what am I doing? That. Sum of j squared from j equals 1 up to 1. What's that equal to? 1. Yeah, it's just 1, isn't it? And is that equal to a 6th times 1 times 2 times 3? Is it? Yeah, it's a 6 times 2 times 3, which is just 1. So yeah, that's just a simple verification, just a simple observation. So the formula does hold true for n equals 1. So we haven't needed our maths brains yet. It's just automatic. And the next step is automatic. Assume the result is true for some value of n. Let's, you know, we could just call it, we could just say for some n bigger than or equal to 1, but it often helps just to introduce a second name. So we're assuming that the result is true for some value k bigger than or equal to 1. And now we wish to deduce from this, and I believe it's helpful to give a good narration to your solutions like this, to put in the explanatory steps. Don't just boil everything down to the equations. it definitely helps to keep the narration in there, keep reminding yourself of it, because that's the logic that lies behind the argument. If you just get rid of all the English and just look at a bunch of equations, it's very hard to see what the argument is. So we're assuming the result is true for some n equals k, and now we wish to deduce from this the result for n equals k plus 1. But just saying you're assuming the result isn't enough. Actually write it down. Write down explicitly exactly what it is you're assuming. So, i.e., we assume that for this special value of n, k, we're assuming that the result holds true for that. We get a sixth of k times k plus 1 times 2k plus 1. We're assuming that's true for the moment. And we want to derive the result for n equals k plus 1. Well, we have to establish this equation when n equals k plus 1. Well, what's it going to look like? Well, the left-hand side is going to be the sum from j equals 1 up to k plus 1 of j squared. Now, as I said yesterday, we're about to set out on a journey here. But if you want to set out on a journey, it helps to know where you want to get to. So I'm going to build a chain of equations. I'm going to do some stuff here, but I ought to keep a very clear eye on where it is I want to get to. And I can even be so, and I can do this because I'm quite, I'm qualified. But I can even, put my money where my mouth is and say I'm going to finish at this point here. And what am I going to finish with? A sixth. See, the result when n is k plus 1, I'm going to finish with the sixth of k plus 1 of k plus 2. And so it's 2n plus 1. So that's going to be 2k plus 3, isn't it? That's the right-hand side of the result. Now, I could have shot myself in the foot because it might take a few more lines than that, but hopefully not. Okay, so hopefully I can get from here to there. Okay, and of course, just as I drew yesterday, I can't just get from here to there on my own. I need to use the assumption somewhere. Use here somewhere. Okay. You probably, you won't be able to do it unless you make use of this. And then you make the key observation, well, these sides are almost the same. Okay. So I should exploit the fact that those two left-hand sides are almost the same. This left-hand side says add up a load of squares until you get to the value j equals k. This one says add up a load of squares until you get to the value j equals k plus 1. So this one just goes one step further than that one. So actually write that down. Actually point that out. This thing here is equal to this. It's pretty much that, but just with an extra bit added on with the square of k plus 1 added on. Because the square of k plus 1 is the final value of j that you consider in that sum there. So that's true on its own. That's just, you're just using the meaning of the summation symbol here. Say that this sum is this sum plus the last term. But now it's clear how to use the assumption. Because here I've got the left-hand side of the assumption sitting here, so I should just immediately replace it with the right-hand side, because then I will have used it. And having stuck the ingredient in, if I mix it around a bit, I should get the results I'm after. So I use this now. I make this switch here. So instead of this sum here, I now write down a sixth of k plus 1, 2k plus 1. So that's from the assumption, and then I've still got my k plus 1 all squared here. So I need to indicate what I've just done then, and this is by the above assumption. And it's pretty clear what assumption I mean, because I've got the word assume here and I've got a big red box around it. It's not as if there's a million other assumptions, so that's enough justification. But in your answer, when you're writing down these solutions, make it clear to the reader what's going on. So you've done this move. This is just manipulating the summation symbol. Oh my God, he suddenly switched, he or she has suddenly put this down instead of that. Why can they do that? Oh, they've used this assumption above. And they've assumed that, so they're allowed to use it. Okay, well, this is looking hopeful now. Because I look at where I'm trying to get to. I'm trying to get to this thing, and that thing's a polynomial in k. If you think of it multiplied out. What kind of a polynomial? It's a k by k by k. So it's going to be a cubic polynomial. It's something k cubed, something k squared, something k, and maybe a constant. And is that what this is as well? Well, that's a quadratic in k, but this bit is cubic in k. K, k, k. So the whole thing will be a cubic in k. So it looks like I'm on the right track. So now you start to manipulate this. So now it's just about some efficient algebraic manipulation. The first thing I draw attention to is the fact one of these factors here, see this thing is fully factorized down here, but one of the factors k plus 1, you can already see it up here. So there's a k plus 1 here, and there's 2 factors of k plus 1 there. Yeah? So we can pull out that factor already. So that would help get us towards our goal. So I would factorize this as k plus 1 into 1/6 of k of 2k plus 1, writing down the other factors. And then you have another factor of k plus 1 here, because it was squared, but you've taken one of them out. That's good. So this is starting much more now to look like this. So they've both got the factor k plus 1 there. Maybe I should try and extract the 6th. I can see the 6th here already. Now, it doesn't look like there's a 6th there, but I can easily arrange that there be a factor of a 6th there. So I can next pull out my 6th. So it's easy to pull a 6th out of this because I just leave behind the k and the 2k plus 1. And I can arrange that I pull a 6th out of this. I just have to write down 6k plus 6. Just have to leave 6k plus 6 behind. So if you multiply in the 6th, you see that you get back to here. This is even better now. Now I've got 2 of the factors. 2 of my factors here. I need some other factors. I need a 2k plus 3 and a k plus 2. I don't see any of them immediately there. So maybe I should probably try and multiply out this bracket and write the whole thing down. So that's going to be k plus 1 times a 6th times, and you get 2k squared. You get a k here and a 6k there, so it's plus 7k. And you don't have a constant here, and then you've got a constant of a 6th. Well, I think it's the final step. I mean, you can allow yourself to say this is 2k plus 3 by k plus 2. We can observe that that's the factorization of that quadratic polynomial. Okay, multiply those 2 factors together, you get this. So, indeed, I should have been braver. I should have lifted this up a little bit up the page. So I don't need this space now. So this just goes, we can just make that step there. It's just a factorization of a quadratic. So overall, from start to end, what have I done there? Start to end, I've proved this, or I've obtained this equation. I won't quite say I've proved it, because I didn't prove it from the, from from the ground up. I proved it with the help of this assumption. So from that assumption, I've been able to deduce this. But this thing in the box here, in this disconnected box, is exactly the result for n equals k plus 1. That's the important point to observe. This result in the box, in the broken box here, is exactly the result for n plus 1. So that's the result in question for n equals k plus 1. The other thing just to check is this deduction has to be valid for any of the relevant values of k. Because the induction principle says you must show this implication that p of k implies p of k plus 1 for every value of k. Now, I achieved it by doing algebraic manipulation. Did I use any special property of the number k in any of these moves? In any of these moves, is any of them only true for certain values of the integer k, but not for others? Well, no. These moves I've done here, just this multiplying out, this factorizing, that's valid for any, no matter what the integer k is. In fact, it would be true if k was, in fact, any real number, any complex number. All this would still be true. So I haven't used anything special about k. So I have done the induction step for every positive integer k. So we could finish off then by just putting some concluding remarks. So we've deduced, or we've established, what have we established here? We've established here that p of k implies p of k plus 1 for any k greater than or equal to 1. And we've already, at the top of the page, we've started out by establishing the base case. So the fact we've established the base case, we've established this linking step. So now it's this property of the integers, the fact that they all line up in a row, beginning with 1, moving on to 2, moving on to 3. You keep adding 1, you move through all the positive integers. So the induction principle says that we can now deduce that the statement p of n is true for every positive integer. So by induction, we now know that the result is true. The sum of the squares from 1 to n is indeed equal to a sixth of n plus 1 of 2n plus 1 for every n bigger than or equal to 1. Okay? It's just the final concluding remark. So that, okay, any questions about the layout of the induction proof or about any of the individual moves in it? But you can see how much is standard. Doing the base case, which should just be an observation. Making the assumption. Declaring that you're going to try and prove the next one. Making your assumption explicit by putting my red assumption box at the top there. Making the assumption plain, very clear to see, unmistakable assumption. Setting out what you're trying to do, working on it a bit, and as soon as you can, or in the most sensible way, bring in the assumption, apply the assumption. That's what happened in this crucial step. Really, all that was, you could say, making this step here at the top, bringing in the assumption, then the rest just flows. The rest is just, algebraic manipulation. But this was the crucial move to make at the start. Okay, linking together the assumption you've made and the result you're trying to prove. Okay. So with the example I did last time, which was question 1, with that example, question 2, what I'd like you to do for the tutorials next week, and we can discuss the solutions and talk about them and look at any problems you had, is achieve the same thing for the other questions. Okay. Now you've got your own notes there, and I'll scan these and put these up on Moodle as well. I normally post them into the comments under the video recording. Let's check that's still going. Yeah. Now, let's just look over the problems I want you to work on. This other one is it's a slight modification of one, just adding up. Actually, how could you describe that summation? Adding up. What are you adding up between 1 and n? Just adding all the odd numbers, did you say? Yeah. Who said it? Yeah. Still can't see it. Odd numbers. Yeah, good. Just adding all the odd numbers between 1 and n, that gives you the square of n. That's pretty nice. I'm sure I've seen that before, but I'm a bit surprised and new by it. If you add up all the odd numbers from the starting point to an end point, you get the square at the end point. That's pretty interesting. So you can prove that by induction. Okay. It should look quite similar to the proof for question 1. You're still adding up order 1 terms. Problem 3 is about the sum of the cubes. What kind of again, you get a polynomial in n. You get a quartic, a degree 4 polynomial. You can start to see a pattern here. When you add up all the integers, you get a quadratic in n. When you add up all the squares, you get a cubic. When you add up all the cubes, you get a quartic, an order 4. So when you add up all the powers of the integers, you seem to get a polynomial of order 1 higher than the orders that you're adding up, than the order of the powers that you're summing. Again, you can spot that pattern in question 5. Adding up again, okay, adding up every integer, the form 3j minus 1. That's an order 1 term you're adding up. Again, you get a quadratic polynomial. I'll kill myself with this wire. 6 and 7 are slightly different. 6 and 7 aren't about establishing an equality. They're about establishing an inequality. Now, inequalities, doing these induction type proofs, they can sometimes be harder to establish. So if you think about it, I mean, where was the nuts and bolts of the proof? The nuts and bolts of this solution was happening here. But that just involved moving from one equation to another equation. If you think about it, when you're moving through equations, you're extremely restricted because you have to pass to something that's the same as the previous expression each and every time. So actually, you're extremely restricted in the kind of things you can do. However, when you're trying to prove 6 or 7, because they're inequalities, when you lay out the induction proof, you'll be passing through inequalities here. Now, passing through inequalities is a bit freer. There's more things you can do, because all you have to do at each stage is move to something bigger if you're doing less than inequality, or move to something smaller if you're trying to establish a greater than inequality. So in some ways, that's good, because you think, oh, I've got more choice. I can do what I want. But when you're trying to do mathematics, that makes it harder, because you've got more different things to choose from. You've got a wider range of possibilities. So in order to select the right possibility, it's harder. Here, really, your hands are tied completely, because you can only essentially pass through the same thing. So really, you can't do anything if you think about it. When you've got to pass through inequalities, you have to choose the right inequality. So that's kind of hardest. You have to be more creative, more mathematically creative or precise to do 6 and 7. Okay. So there are interesting inequalities relating So 6 is relating the nth power of 1.5, relating that to 1 plus n over 2. And the other inequality is relating the power of 2, so this thing, which is going to grow exponentially, relating it to a ratio of factorials. Okay. Now, maybe for some of these, you might need to use the so-called extended induction principle, or the strong induction principle. This is something which is equivalent to the type of induction we've just been doing. The type of induction we've just been doing is where you establish the base case and then prove the linking step from n equals k to n equals k plus 1. Strong induction is a different way of doing it. What you're doing is you're not doing a linking step from n equals k to n equals k plus 1, but you're doing a linking step from the assumption that P is true for all the values, 1 through k plus 1, showing that the assumption of the truth of all of those implies the truth of the next one. So for more complicated situations, you have to call, in order to establish P of k, you have to call on the truth of all of the previous statements. Okay. Now, it's still the same. It's an equivalent principle to the principle of normal induction. Okay. Okay. So what I just want to end on, I'm going to finish a few minutes early because I've got a meeting to go to over in the Burley building. So I'm going to have to hop on my bike and zoom over there for 1 o'clock. But what I'd like to finish with is just showing you, so we've seen a number of interesting results there. The sum of the integers, a formula for the sum of the integers, a formula for the sum of the squares, a formula for the sum of the cubes, and so on. And you see, we get this nice, these nice polynomials which, and it kind of reminds us of the process of integration. Remember, summation is linked with integration. So summation is a discrete analog of the integral of a continuous function. And of course, you all know that when you integrate x to the power n, you get something which is x to the power n plus 1 divided by n plus 1. But the point about it is when you integrate something of order n, you get something of order n plus 1. And that's the same thing that's going on here. When you sum something of order n, or order, I won't call it n because the n's up here. When you sum something of order 2, you get something of order 3. You sum something of order 3, you get something of order 4. So there's that same feature happening. So we could ask ourselves our questions, well, okay, if that's going to be true, how do we go about finding these polynomials here? You know, how was it that I knew that these were the correct polynomials to write down here? How did we discover those? In one case, knowing what the right one is, you can then try and go and establish it by proof by induction. But how do you figure out what the correct polynomial is? So that's what I'd like to show you, how you can, or a technique to identify what the correct polynomial is. So it's in this, when you look on MATLAB, you'll see my lecture slides. It's in these lecture slides that I was using the other day. Wait for these to come up. And the second last one. You're looking at these lecture slides. Sometimes the math notation is messed up, but you just reload the page and it should load back correct. It's just to do with the web service that does the typesetting. Okay, so there we talked about induction. So this is what I was telling us here. So I talking about integration, it says that intuition tells us, oh, so what am I doing here? Here I'm looking at the sum of the fourth powers. So could we find the polynomial that gives you the sum of the fourth powers? Could we find that polynomial? It looks a bit funny. Anyway, no matter. Well, here's a way we could do it using the computer. Now here I'm using this online software, Sage. You can get to it by, well, when we display the result here, there'll be a link that you can get to it. When you go and look at these slides, you can see this little bit of code I've written. Now I've had to set some things up here. This first line, so just very briefly talk to this. This first line just defines 6 symbolic variables. So they're going to be the coefficients in my general quintic polynomial, my general order 5 polynomial. I've defined a function f there. What does that function f do? I'll make it a bit bigger. The function f is the summation. So the f of m returns the sum of I to the power 4 for I in the range 1 to n. So the function f is this object here. The function g is the quintic polynomial. So g of m returns a constant plus a1m, a2m squared, all the way up to a5m to the power 5. So f is the left-hand side of the summation. G is, well, g at the moment is just a general quintic. And what I do is I generate, now the quintic is defined by 6 unknowns, because the quintic has 6 parameters. Constant, 6 coefficients, the constant coefficient, coefficient a1 all the way up to a5. So if I've got these 6 unknowns, I'm going to need 6 independent pieces of information to try and determine them. So I then had this equation, and I set up the equations f of m equals g of m for m in the range 1, 2, 3, 4, 5, 6. So this command here sets the EQS variable, the equations variable, to be this set of 6 equations. And then I basically ask the computer to just solve the equations with respect to the 6 variables. And there's a bit of programming nonsense here. Solution dictionary equals true. I store what's called a solution dictionary in this variable solve here. And then I just want to show the equations and show the solution. And again, this is just a bit of programming gubbins, but basically substitute the solution back into the polynomial. If you have a look at this, if you have a look at the results of this, you'll see what's going on. So here's the results of it displayed here. So first we've got, you see this box is zooming off the page. First we've got the 6 equations. So this first equation is just the equation when m equals 1, when the upper limit equals 1. So you got 1 is just the sum of the first 1/4 powers. That's just equal to the sum of the coefficients. 17 is 1 to the power 4 plus 2 to the power 4, 1 plus 16. So 17 is equal to that general quintic where m is equal to 2. And so there's just a big long set of equations there, all the way up to 2275 is the sum of 1 to the power 4 plus 2 to the power 4, etc., all the way up to 6 to the power 4, or whatever, 5 to the power 4. It solved the equations, and these are the solutions. A0 was 0, A4 was a half, and so on. So that's what the polynomial looks like there. Okay. So using this principle, well, really at the moment it's just an assumption that the sum of the 4th powers should be a quintic. If that's true, then the quintic has to be this. Okay. The quintic is defined by 6 parameters. I look at 6 instances of the equation, solve for the 6 parameters, and I get these values for the coefficients. So assuming that the sum of the 4th powers is a quintic, if that's true, it has to be this quintic, this order 5 polynomial. So once we've discovered this, we can then go and establish it using proof by induction in a very similar way that I established the one for the sum of the squares. Do the base case, which will just be a trivial observation. Assume it's true for n equals k, prove it's true for n equals k plus 1. Now, because you're up to order 4 and order 5 here, the algebra will be long and messy. You got to handle these coefficients, 1/30th. So, you know, it'll be awkward, but in principle, it'll be doable. And, you know, you can easily extend this process to any power as well, any order as well. Okay, so let's finish there. And next week, so I'll be taking you in the 2 tutorials next week. Andy took you this week. I'll take you next week, and we'll focus on these induction problems. Okay? And if you want to go and experiment with this code, just go to Moodle and bring up these lecture slides, and you'll be able to use the code there.